As we explained earlier, if we have a string that's tied at both ends, like here and here, at the fundamental frequency, it's going to oscillate with a node at both tied ends and an antinode in the middle. Remember, the nodes are a physical restriction just because the string is tied here, these two nodes here. And the antinode is going to be halfway between the nodes in this case. At this frequency, the string is going to oscillate with a high amplitude. So this is twice the amplitude. And remember, what we see here is actually half of a wave. The other part extends a little bit in the outside of the slide here, and then the other half of the wave reflected here, or move in this other way. Now, because of that, the length of the string is equal to lambda over 2. We are looking at half of a wavelength. The interesting thing is, a string normally would not oscillate only at that fundamental frequency. Actually, that's the beauty of musical instruments. Musical instruments usually would oscillate at a combination of what we call harmonics. And that's what's going to give the particular note of a musical instrument, is the combination of the various harmonics in every string that vibrates. Now, fundamentally, after the fundamental frequency, which we also call the first harmonic, we can have other harmonics that are multiples of that first harmonic. The harmonics are related through a very easy relationship. Harmonic 1 is n1 times the fundamental frequency. Harmonic 2 would be 2 times the fundamental frequency. So let's say this first one is oscillating at 10 Hertz. Then the second harmonic would be 20 Hertz. The third harmonic would be 30 Hertz, and so on. Okay. So now let's look more closely at the other harmonics. There is a physical constraint that's the same for all harmonics, that the ends have to be nodes. That's applicable to all. That's a physical constraint. That's because the string here is tied at both ends. Now, the second harmonic is going to happen when we can fit another node within the string, which is going to be in the middle. The third harmonic when we fit 2 nodes, 2 additional nodes. Fourth, 3 additional nodes, etc. Now, whenever we fit an extra node, that's going to impose another restriction on the string, making the oscillations at a lesser amplitude. So you see, the more middle nodes we have, the smaller the antinode. So these, remember, halfway between 2 nodes is an antinode. And the antinodes get smaller and smaller as the harmonics get higher. The other thing that you need to remember, the length, we call this a segment, the length of the distance between a node to the next node, or what we call a segment, is the wavelength over 2. So if we can physically measure that length, like with a ruler, then we immediately know what the wavelength is. Lambda over 2 is equal to that length that we measured. So for example, if we look at this, we have 1, 2, 3, 4, 5 segments. 5 segments that's 5 times lambda over 2. That should be equal to the length of that particular string, the overall length. So from here I can find lambda. Lambda is equal to 2L over 5. Notice that we have that in this expression here. Lambda 5 for the fifth harmonic is twice L over 5 the fifth harmonic. Be careful though, don't memorize this equation for all standing waves. You'll see later on that's not applicable in all cases. It's applicable for the cases when we have the string tied in both ends. And you'll see it's applicable also when it is open at both ends, when it is free at both ends. We'll get into that later. Okay, so now we can very easily figure out the wavelength by knowing the length of the string. The frequency or the velocity, we can know one or the other through this equation. If I know the frequency, I can know the velocity, or vice versa. If I know the velocity, I can know the frequency once I measure lambda.